more sections, and first one is the we consider is the effect sequential space. Okay, and here we consider more practical issues. The Earth is not perfectly spherical, and actually it exists a very small eccentricity, which means the radius in the equatorial plane is not the same, actually a little bit longer than from the center to the North Pole. So here for Earth, and let me define this is AE, and this is center, this is the GE. So for Earth, the AE equal to 6378, and this is the number we use in all the exercise and our test. And for BE, that actually is 6356.785 kilometers. Okay, so that means this one producing corresponding eccentricity is about 0.08182. Okay, so not the Earth is not perfectly sphere. Okay, so under these situations, and really we've been thinking they should have occupied focus. Okay, and so in these situations, let me demonstrate how to consider these kind of imperfect surface shape, and then into how to correct our calculations. So to that purpose, let me exaggerate the drawing here. So for example, here let me put the Earth into I exaggerate the conditions. So this is the center, and this is the focus. Okay, I would say this is the focus of the. We visualize this as a vertical. Earth. So under this kind of definitions and how we define our latitude, okay, and the latitude, for example, here we consider a site here, and so we're connecting on the focus to here, and this is the radial directions. So this is the local horizon here. So this is normal, okay. And in reality, what we measure our latitude is from here. Okay, so that is a way, and we're doing this one. And under these situations, this is the and this is a name for this, and they call it geodetic latitude. But basically, I can tell you the L is L is the latitude we are commonly used in map or in whatever the exercise, and that is the angle we refer to. And so under these situations, then here I want to do certain corrections. So, for example, here corresponding to a sphere, so this is the corresponding spherical shape, and taking AE as the radius. Okay. So in before we assume this is the spherical, this is the perfectly I would say circular. Okay, we simply look at the cross section. So this is perfectly circular. So in our previous exercise, we always assume that is the using the blue as the profile for describing the locations and coordinates on the surface. But here, actually, we are not. So here we want to do the certain corrections. So here we can do something here. So let me give this point with the certain coordinates. So let me say this is the let me see. Let me give this coordinate and say this is the coordinate system X and this is the coordinate system Z. Okay, so this point has the coordinate XZ. And in three-dimensional, I want to emphasize that XZ actually is this. So this is the equatorial plane, and this is the I-axis and J-axis, K-axis. So for example, here we have a side here. Okay, so that point, basically the two are the same point here on the Earth's surface. And here we take the nomenclatures for XZ is this. We simply take is so we simply take the projections of this point onto the IJ plane. So basically this distance is X and the vertical distance is Z. Okay, so that is a 3D view from what we see here, and this is the cross-sectional view. Okay, so later on we will further decompose the X component into I and J. So keep this in mind. Right now we're working on this one. So for this case, we are given is L, which means we given the measured latitude, and we want to find is X and Z in terms of this kind of situations. So from here we can say is this, we simply taking the projections. Okay, so this point is a projection of that one onto the x-axis. So from here we can see pretty easily in this way x is simply equal to the cosine of this distance, and this distance is let me put a extensions of that one to here. So that is corresponding. This is our radius AE. So AE basically equal to this one. AE equal to the radius of this and also equal to this. So this is AE. So from here you can see basically this one. Get rid of this one. Okay, so XZ are measured in this way. So from here we can apparently we can see X equal to simply is AE times cosine. And cosine, which this one, let me say this is the beta. Okay, and sine E and Z is this one, and actually Z from here you can see. So to calculate, to determine it, we can see if this is a circle, and say if at any point, say here is the xy. So circle, for example, here we have the formula x equal to a squared. So here, so for example, if we give any distance x, then basically we can say y equal to the a squared minus x squared. So this is y on a circle. Okay, and if corresponding to the circle, we consider ellipse. So this is the ellipse. And ellipse for this case, say this distance, say this is b. So we have the equation is x squared over a squared plus y over b squared equal to 1. Okay, so here we can say y will be equal to 1 minus x squared a squared, take a square root b. So let me rearrange this one, and b over a, and a squared minus x squared. Okay. So that means if we given the same value of the x, and this is a corresponding measurement of the y onto the corresponding elliptic ellipse. So compared to here, you can see, let me use the color B, y on the ellipse compared to the y on the circle. Would that be equal to, compared to this one, that is the b over a and a squared minus x squared, and this one is a squared minus squared, right? I simply compare the two values. Okay, so from here you can easily see basically they have a ratio b over a. So taking this option, you can see corresponding, if we consider a circle and the corresponding ellipse and fitting there, so basically their y value simply is a ratio of b over a. So taking that one to here, from here you can see basically z value is a corresponding vertical distance and corresponding to the circle. So from here we can see easily that is b e over a e times sine beta, right? so from here I simply is derived is say the vertical distance in the lab simply is b over a times the vertical distance in circle. So this value corresponding to our value is this thing here, right? Okay, so we have this one. So z simply can be expressed into b times sine beta. And if you wish, and because usually we are given the Earth, given the Earth's radius is the AE. So if you like, you can express into AE, and that is AE times 1 minus E squared sine beta. Okay. So here I will add one more eccentricity. So usually we can convert, because right now the beta is not known yet, but there are two useful information connecting beta to the given value. And let me directly give you the result. And these results are from our textbook. Okay. So useful formula is this sine beta can be described by all the given information is sine L and 1 minus E squared sine squared L. So this is the first one. And then cosine beta. Okay, so those are in our textbook, from the textbook. And I skip off the detailed derivation. I think that occupies more than 1 page. It's not important, we don't keep using it. So therefore, from here we plug in, there we have x will be equal to AE and cosine L. 1 minus E squared sine squared L, and Z will be equal to AE 1 minus E squared sine L, the same denominators. And the two equations are not useful yet, and we can further do a little bit more. So with the two informations, and we can add it up a little, one more term here, and then do the color. So right now looking here, and basically what we calculating is the certain information about a point on the Earth's surface. And so if based upon this one, say for example this is a radar site here. And so from radar side, we can see the radar can always measure the radial distance. For example, this is, I would say, I exaggerate. Okay, so this is the space, and say this is our satellite. And we can measure the satellites, for example, the distance from here to here, and per our textbook notation called h. Okay, so basically we can extend that information to consider the measurement of the sat. So consider this one, you can see if this is h, and simply projecting into the two components. Let me call this is delta z, and this is delta x. Basically, delta z is h times cosine L, right? And delta x is h times, this is sine L. This is cosine L. Okay, so for example, if we consider the measurement of the satellites, can I add it up here? So here for satellites, basically this one is adding delta x, right? And delta x will be equal to that number. So here basically is h times cosine L, right? And this one basically added up is delta z, and delta z is replacing by h times sine L. Okay. So from here we have the descriptions of the two quantities x, z for a satellite. So here it really depends on which point you want to do it, and you can continue add up this one. So now we have the information, so we want to convert into IJK. So now to convert, the calculated x, z informations into the coordinates in IJK system. So I'm going to use this one. So for example here, let me say that is the angle here. So say if this is a theta, the local sidereal time of the site. So with that information, we simply take the projecting x, this is x, we simply projecting x into the two components. So basically this one is x sine theta, this is x cosine theta. Okay, so therefore, given this point, and let me say this point, the arc of, for example, satellites for this information, then basically that one can be described by x times, is that right? X cosine theta and x sine theta and z in IJK. Okay. So again, this formula provides us a little bit more refined descriptions, and so it depends on how more accurate you want to go forward. Either you can consider added up this kind of correction, which means consider the eccentricity of the Earth, or otherwise, if we simply consider its perfectly spherical shape of the Earth, then we simply just using whatever the information before. Okay, so this section basically provides us a little bit quick things here. Let me see, we should have one example. So we can exercise one example.